Alright, in this video we're going to go over a couple of the questions from the Chapter 5 quiz review. So in question number 1, they give us this table of values, and as we read through this, in the end what they're asking for is a right Riemann sum with the 3 subintervals from the data. So anytime I'm asked to do a Riemann sum based on a table, I always like to draw a picture. So I'm going to go ahead and draw myself a little picture here. So it doesn't have to be accurate in any way, it's just to give me something to talk about, something to help my brain see what's going on here. So input of 4, output of 6.5, input of 7, output of 6.2, input of 12, output of 5.9, and input of 15, output 5.6. So then I go ahead and draw my right endpoint rectangles because that's what they asked for. So my first interval is from 4 to 7, so the right endpoint of that is at 7. Then my next interval is from 7 to 12. The right endpoint of that is 12. Over make my rectangle. Next interval from 12 to 15. The right endpoint there is 15, so that's where I get the height of my function, or of my rectangle from. And then it's just a matter of finding the area of each of those rectangles and adding them up. So my first rectangle has a height of 6.2, the function value at the right endpoint, and a width of 3. My next rectangle has a height of 5.9, the function value at the right endpoint, and a width of 5. And my third rectangle has a height of 5.6 and a width of 3. Notice that we did not ever use the input of 6.5 because that's never a right endpoint. And we're only interested in from 4 to 9. So that's just not part of our problem. So I add all that up and I get 64.9. Thinking about my units, because the R values, the heights, are liters per hour, and the T values, the width, are hours, multiply that together and we just get liters. And so we say, oh, okay, the answer is 64.9. That's the first choice here. But that's not actually the correct answer. Because if we go back and read the question says, using a right Riemann sum with 3 subintervals, what is the approximation for the number of liters of oil that are in the tank? Well, this is just the liters that have gone into the tank, because we're pumping oil into the tank. And so we've added 64.9 liters from time t equals 4 to time t equals 15. But we started with 50. So the number of liters in the tank is 64.9 plus 50, which is 114.9. Because we started with 50 and then we added to that 64.9. The 64.9 is just how much we've accumulated because we're pumping oil in. All right, so that is the first question. Question number 2, go ahead and get rid of all this. Of course, you can pause, rewind, go back if you need to see that again. Question number 2 gives us this definite integral from 0 to 4, which this would be, of course, the exact area underneath f of x from 0 to 4. And so this is asking us, okay, we've got 5 different options for the picture. Well, in which of these options would a left endpoint rectangle approximation overestimate the actual value of the area underneath the curve? And we can draw some pictures, of course, and see, what that will look like. We also have just basic rules. Let me make this way bigger here for a second. If my function is decreasing, actually let me double check here. Are we going from 0 to 4? Yeah, 0 to 4. If my function is decreasing, the left endpoint will overestimate. The left endpoint will overestimate. And I think we've got one more that's increasing here at the end. So yeah, we have E is increasing, so that doesn't apply. If the function is decreasing, as it is in A and C, then the left endpoints will overestimate. If the function is increasing, as it is in B, D, and E, the left endpoints will underestimate. And here's my first rectangle here. Oops. Here's my first rectangle. It's right there, 0. Then my next one, underestimating. So left endpoints would overestimate if the function is decreasing, so that's A and C, and then left endpoints would underestimate if the function is increasing, and so that then is B, D, and E. Whoops. And then, of course, right endpoints are just going to be the exact opposite of that. If I were to draw a right endpoint, my right endpoint will underestimate if the function is decreasing and overestimate if the function is increasing. So it's just flipping all the answers once we switch to right endpoint. So a right endpoint would overestimate if the function is increasing, like in B, D, and E, and it would underestimate if the function is decreasing, like A and C here. And then lastly, we have trapezoids. And with trapezoids, remember that the rule is the trapezoid's overestimate versus underestimate is based on whether the function is concave up or concave down. So let's look at a little bit of a picture here. Let's get rid of some of our rectangles. All right, so if I were to draw a trapezoid for the first one, let's say I'm going to go from 0 to 2. Hard to see, not a perfect drawing by any means. But that trapezoid is going to go over the function here because we are concave up. The same will be true when we have a concave up but increasing function. It's going to be a little bit over the curve there. But if we have concave down, it doesn't matter if we're increasing or decreasing. Let me make it a little bigger, easier for me to draw here. If we're concave down, oops, and I'm just making my rectangle or my interval width a little bit wider so that it's easier to see. So I'm going from 1 to 3. We're going to be a little bit underneath this curve. Okay. And my lines are squiggly. I know it's terrible, but concave up, a trapezoid is an overestimate. Concave down, a trapezoid is an underestimate. And you can see that that is regardless of whether or not we have an increasing or a decreasing function. So trapezoids would give an overestimate if the function is concave up, like it is in A and C, or sorry, A and D, excuse me. And then E is weird because it's not concave up or concave down, it's linear. The second derivative would just be 0 the whole time. And the trapezoid would give an exact answer. If you make a little trapezoid here from 1 to 3 again, Well, that's exactly the function there. So that's not an overestimate if it's the exact answer. All right, so that's questions 1 and 2. Moving on then to question 3. So here we actually have an equation. So we have f of x equals 9 to the x, and we're supposed to find our right Riemann sum with 4 subintervals. Just like with the table, I think the picture is helpful here. So I'm going to do a quick sketch. Like I said with the table, it doesn't actually matter how accurate I am. It's just giving me something to think about. But I do know what a basic exponential function looks like, so I can do a reasonable picture here. And we're going from 0 to 2. So if I cut that into 4 chunks, figure out what my width is, what my delta x is. It's the width of the interval, 2 minus 0, divided by how many chunks. So that gives me 1/2. So then we're going to cut this into equally spaced chunks with a width of 1/2. So we've got 1/2, 1, 3/2, and 2. And we're using, in this case, right endpoints. So let's just go ahead and sketch those here. So right endpoint rectangle, right endpoint rectangle, right endpoint rectangle, right endpoint rectangle. And I know that the width of all of these is going to be 1/2, so it's just a matter of finding what those right endpoint function values are. And that's just figuring out what is the function value at each of the right endpoints. And so it's just 9 to whatever power. 9 to the 1/2, 9 to the first, 9 to the 3/2, 9 to the second. So we'll go ahead and write that down. So it's going to be 9 to the 1/2 plus 9 to the first plus 9 to the 3/2 plus 9 to the second, all times 1/2, just factoring out that width. If we multiply that all out, I believe we get 60. So hopefully not too bad there on that one. Moving on. Here we go. So we had one really similar to this in our homework a couple days ago. And when we're asked to kind of identify what the Riemann sum would look like, we think about 2 things. One is the width of the subinterval, the width of each rectangle. And 2 is, am I plugging in the correct x values to the function based on which method they asked me to use. So if they asked me to use left endpoints or right endpoints or midpoints, am I plugging in the right things? And so in this case, we're using the 4 subintervals indicated by the data, so I don't know that these are equally spaced chunks. Like in the last one, I knew that each chunk had to be a width of 1/2. Here, they don't have to be equal, but I know that each chunk, its width, is going to be defined just by how far apart are these 2 x values, how far apart are these 2 x values, how far apart are these 2, and how far apart are these 2. And so we can see in each of our expressions, a squared minus 0, that's the first width, 3a minus a squared, that's the second width, 6a minus 3a, that's the third width, and 7a minus 6a, that's the fourth width. And they all have that same piece. So that's the first thing I want to think about, but unfortunately it didn't help me this time because they all did it correctly. Now I want to think about the heights. Okay, what are the heights here? We plugged in the correct things. So because it's right endpoints, a right Riemann sum, my first interval from 0 to a squared, the right endpoint function value is -1. So I'm looking for one of these expressions where the width of that first interval, a squared minus 0, is being multiplied by -1. I see that it happens in 2 of them, but not the other 2. And yours might be scrambled up in terms of the order here. But I know that that first interval has to have a height of -1. And if it doesn't, well, I can go ahead and eliminate that. So no, you've used the left endpoint, the positive one. So have you. So you're out. And as I go through, I can see that those right endpoints continue. So the next right endpoint height should be -3, yes. Then -7, yes. Then -9, yes. So the only difference between these two is whether they're saying it's an overestimate or an underestimate. And because it's a right Riemann sum and the function is decreasing, if I think again about my picture here, draw some decreasing function. If I draw a right endpoint rectangle, that's going to leave some chunk of area out. This little chunk has not been included. So I'm missing some. So it's an underestimate. So my answer is that one. So they have the correct format for the right Riemann sum, and then they correctly identified that because f is decreasing, it would be an underestimate. Similar type question here, identifying which of these correctly represents, this time, the midpoint approximation. So once again, I want to think about, are my widths correct and are my heights correct? And so in this case, it is some number of subintervals of equal width, and since we're going from 1 to 3, my delta x is 3 minus 1, the whole interval, how long is it, divided by the number of subintervals that we cut it into. So that's, again, going to be 1/2, just like it was in the other one. It's not always going to be 1/2, just sort of coincidence that these two both are. So because they're all the same, we can then factor that width out. So we're looking for one of these that has a 1/2 factored out in front, which this one does and this one does. And again, yours might be scrambled up in a different order than mine. But any of the ones with a 1/4 out front, I can get rid of. And now it's just determining, well, which of these remaining ones is using the correct input value for the midpoint method. So again, I'm going to draw a little sketch here. We're going from 1 to 3. So then that's 1.5, 2.5. But I'm not using left endpoints or right endpoints. I'm actually using midpoints here. So this would be 1.25. That's the value that I have to plug into the function and then go up until we hit the actual graph, and then go a little bit left, a little bit right to get my rectangle. So the first input value has to be 1.25. The next one, the midpoint of the next interval, is 1.75. Then the midpoint of the next interval is 2.25. Midpoint of the last interval, 2.75. So that's what I'm going to be plugging into the function. So that's what I'm looking for now. Did I plug the right things into the function? And as I look here, no, we're plugging in 1 and 1.5. Those are the left endpoints and right endpoints. 1.5 and 2, that's the left endpoint and the right endpoint. I need to be plugging in these midpoints. Well, that's this last one. And what they're really asking for here, what this, just to make sure we're understanding, what this thing really is, that's the trapezoid approximation, where you found the height of the left endpoint by plugging in 1, you found the height of the right endpoint by plugging in 1.5, and then you averaged them. Base 1 plus base 2 divided by 2 times the height, which is the width, which is 1/2 here. So they used the wrong method there. They used trapezoids rather than midpoints. All right, I'm going to do the rest in a separate video because we're almost 20 minutes here.